The term black hole is of very recent origin. It was coined in 1969 by the American scientist John Wheeler as a graphic description of an idea that goes back at least 200 years, to a time when there was two theories about light. One, which Newton favored, was that it was composed of particles. The other was that it was made of waves. We now know that really both theories are correct. By the wave and particle duality of quantum mechanics, light can be regarded as both a wave and a particle. Another theory that light is made up of waves. It was not clear how it would respond to gravity. But if light is composed of particles, one might expect them to be affected by gravity in the same way that cannonballs, rockets, and planets are. At first, people thought that the particles of light travel infinitely fast, so gravity would not have been able to slow down. But the discovery by Romer that light travels at a finite speed means that gravity might have an important factor. On this assumption, a Cambridge Don John Mitchell wrote a paper in 1783 in the Philosophical Transaction of the Royal Society of London, in which he pointed out that a star that was sufficiently massive and compact would have such a strong gravitational field that light could not escape. Any light emitted from the surface of the star would be dragged back by the star's gravitational attraction before it could get very far. Mitchell suggested that there might be a large number of stars like this, although we would not be able to see them because the light from them would not reach us. We would still feel their gravitational attraction. Such objects are what we now call black holes, because that is what they are, black voids in space. A similar suggestion was made a few years later by the French scientist Laplace. Interestingly enough, Laplace included it in only the first and second edition of his book, The System of the World, and left it out of later editions. Perhaps he decided that it was a crazy idea. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory, and according to the wave theory, it was not clear that light would be affected by gravity at all. In fact, it is not really consistent to treat light like cannonballs in Newton's theory of gravity, because the speed of light is fixed. A cannonball fired upward from the earth will be slowed down by the gravity and will eventually stop and fall back. A photon, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? A consistent theory of how gravity affects light did not come along until Einstein proposed a theory in 1915. And even then it was a long time before the implication of the theory for massive stars were understood. To understand how a black hole might be formed, we first need understanding of the life cycle of a star. A star is formed when a large amount of gas, mostly hydrogen, starts to collapse in on itself due to its gravitational attraction. As it contracts, the atoms of the gas collide with each other more and more frequently and at greater and greater speed. The gas heats up. Eventually the gas will be so hot that when the hydrogen atoms collide, they no longer bounce off. But instead causes it to form helium. The heat released in this reaction, which is like a controlled hydrogen bomb explosion, is what makes the star shine. This additional heat also increases the pressure of the gas until it is sufficient to balance the gravitational attraction and the gas stops contracting. It is a bit like a balloon. There is a balance between the pressure of their inside, which is trying to make the balloon expand, and the tension in the rubber, which is trying to make the balloon smaller. Stars will remain stable like this for a long time with heat from the nuclear reaction, balancing the gravitational attraction. Eventually, however, the star will run out of its hydrogen and other nuclear fuels. Paradoxically, the more fuel a star starts off with, the sooner it runs out. This is because the more massive the star is, the hotter it needs to be balance its gravitational attraction. And the hotter it is, the faster it will be use up its fuel. Our sun has probably got enough fuel for another 5,000 million years or so, but more massive stars can use up their fuel in as little as 100 million years, much less than the age of the universe. When a star runs out of fuel, it starts to cool off and so to contract. What might happen to it then was first understood only at the end of the 1920s. In 1928, an Indian graduate student, Chandrasekhar, set sail for England to study at Cambridge with the British astronomer Sir Eddington, an expert on general relativity. According to some accounts, a journalist told Eddington in the early 1920s that he had heard there were only 3 people in the world who understood general theory of relativity. Eddington paused, then replied, "I am trying to think who the third person is." During his voyage from India, Chandrasekhar worked out how big a star could be and still support itself against its own gravity after it had used up all its fuel. The idea was this: when the star becomes smaller, the matter particles get very near each other, and so according to the Pauli exclusion principle, they must have very different velocities. This makes them move away from each other and so tends to make the star expand. A star can therefore maintain itself a constant radius by a balance between the attraction of gravity and the repulsion that arises from the exclusion principle. Just as earlier in its life, Chandrasekhar realized, however, that there is a limit to the repulsion that the exclusion principle can provide. The theory of relativity limits the maximum difference in the velocity of the matter particles in the star to the speed of light. This means that when the star got sufficiently dense, the repulsion caused by the exclusion principles would be less than the attraction of gravity. Chandrasekhar calculated that a cold star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. This mass is known as the Chandrasekhar limit. A similar discovery was made about the same time by the Russian scientist David Boch. This had serious implications for the ultimate fate of massive stars. If a star mass is less than the Chandrasekhar limit, it can eventually stop contracting and settle down to possible final state as a white dwarf with a radius of few thousand miles and a density of hundreds tons per cubic inch. A white dwarf is supposed by the exclusion principle, repulsion between the electrons in its matter. We observe a large number of these white dwarf stars. One of the first two we discovered is a star that is orbiting around Sirius, the brightest star in the night sky. Landau pointed out that there was another possible final state for a star, also with a limiting mass of about 1 or 2 times the mass of the Sun, but much smaller even than a white dwarf. These stars would be supported by the exclusion principle, repulsion between the neutrons and protons rather than between electrons. They were therefore called neutron stars. They would have a radius of only 10 miles or so and a density of 100 millions of tons per cubic inch. At the time they were first predicted, there was no way that neutron stars could be observed. They were not actually detected until much later. Stars with masses above the Chandrasekhar limit, on the other hand, have a big problem when they come to the end of their fuel. In some cases, they may explode or manage to throw off enough matter to reduce their mass below the limit, and so a white catastrophic gravitational collapse. But it was difficult to believe that this always happened, no matter how big the star. How would it know that it had to lose weight? And even if every star managed to lose enough mass to avoid collapse, what would happen if you add more mass to a white dwarf or neutron star to take it over the time? Would it collapse to infinity density? Eddington was shocked by that implications and he refused to believe Chandrasekhar result. Eddington thought it was simply not possible that a star could collapse to a point. This was the view of most scientists. Einstein himself wrote a paper in which he claimed that stars would not shrink to zero size. The hostility of other scientists, particularly Eddington, his former teacher and the leading authority on the structure of stars, persuaded Chandrasekhar to abandon this line of work and turn instead other problems in astronomy, such as the motion of star clusters. However, when he was awarded Nobel Prize in 1983, it was at least in part for his early work on the limiting mass of cold stars. Chandrasekhar had shown that the exclusion principles could not halt the collapse of a star more massive than the Chandrasekhar limit. But the problem of understanding what would happen to such a star according to general relativity was first solved by young American Robert Oppenheimer in 1939. His result, however, suggested that there would be no observational consequences that could be detected by the telescope of the day. Then World War II intervened and Oppenheimer himself became closely involved in the atom bomb project. After the war, the problem of gravitational collapse was largely forgotten as most scientists became caught up in what happens on the scale of the atom and its nucleus. In the 1960s, however, interest in the large-scale problem of astronomy and cosmology was revived by a great increase in the number and range of astronomical observations brought about by the implication of modern technology. Oppenheimer's work was then rediscovered and extended by a number of people. Black holes are one of only a fairly small number of cases in the history of science in which a theory was developed in great detail as a mathematical model before there was any evidence from observations that it was correct. Indeed, this used to be main argument of opponents of black holes. How could one believe in objects for which the only evidence was calculations based on the obvious theory of general relativity? In 1963, however, Martin Schmidt, an astronomer at the Palomar Observatory in California, measured the redshift of a faint star-like object in the direction of the source of radio waves called 3C237. Further encouragement of the existence of black holes came in 1967 with the discovery by a research student at Cambridge, Joyce Lane Bill Burnell, of objects in the sky that were emitting regular pulses of radio waves. At first, Bell and her supervisor Anthony Hewish thought they might have made contact with an alien civilization in the galaxy. How could we hope to detect a black hole? As by its very definition, it does not emit any light. It might seem a bit like looking for a black hole cat in a coal cellar. Fortunately, there is a pioneering paper in 1783, a black hole still exerts a gravitational force on nearby objects. Astronomers have observed many systems in which two stars orbit around each other, attracted toward each other by gravity. They also observe systems in which there is only one visible star that is orbiting around some unseen companion.